Welcome back to this course, Introduction to Blockchain Cybersecurity. This course is a presentation of Coding Bootcamps. This lesson is Introduction to Smart Contract Vulnerability and Attacks, and we're going to discuss how to build secure blockchain applications. So smart contracts and blockchain applications are really one and the same thing, and here we're going to discuss vulnerability and attacks. A little bit about smart contracts is, even though they're called contracts, they can enforce a legal agreement and they can make payments. However, to this date, no court in the world has ruled on the enforceability of blockchain smart contracts. Solidity is a language used on Ethereum and other blockchains for building smart contracts, and we'll discuss some of its characteristics. We'll also go over auditing of smart contracts, which is a very good idea, and go over some management tools. Quite often, but not always, bad application development, bad programming practices are behind a lot of the vulnerabilities in smart contracts. And there's also techniques called re-entry, where there was an unexpected re-entry to a function in the smart contract. Access control, so not knowing who is operating on the smart contract, who the actors are, or a bad identity. Arithmetic problems, unvalidated or unchecked return values. Of course, there's always the denial of service. Weak randomness, and race conditions, which is not only a problem with smart contracts, but they're problems in general, and timestamp dependence that is not consistent with logic. Solidity, which is what this function is written in, has a useful function called a fallback function. However, in this case, once this function withdraws the correct amount, an attacker can run a fallback function and then call this withdrawal again, withdrawing more to a different address until the balance is zero. The same thing again, called access control. So again, it is that fallback function. If the attacker has access to create and call a fallback function, that fallback function can call this withdrawal and keep withdrawing to the attacker's account again until this balance is zero. The integer underflow and overflow is an attack that happens in more than just smart contracts, but here an attacker can take advantage of this to withdraw more than his or her account balance. And the way that this works often is a variable is set up as an integer, and a value that's greater is passed to that integer, which sometimes results in the smart contract wrapping the value as an unsigned integer, and we can see here uint, and you can see here uint again, so unsigned. That would allow for the withdrawals to be greater than what is generally allowed for certain balances. So it could be exploited, and an attacker could end up withdrawing more from an account that's greater than his or her balance. Another type of attack is called bad randomness, and that's attacking functions kind of replying on its unpredictability. So we could see here we're using a random number here in this solidity, and random numbers do have a certain degree of unpredictability associated with them. And we see here that we are sending a balance. So in this case, this could be considered a sloppy method for managing the balance. Same thing here, using the block hash and making a transfer of a balance here. So contracts should always be looked at. The rules need to be evaluated, and any type of randomness should be obviously scrutinized very closely. Here's a denial of service attack, and obviously denial of service is a problem in more than just smart contracts. But if we take a look here, what's happening is the transactor is being shut out, and the miners that are managing these nodes are collecting what are called the gas fees for processing the transaction, but they are taking advantage of the access control here. And we could see here that there's also an issue with the access control. So denying the proper parties access and then essentially pocketing the gas fees is another way that smart contracts are attacked. Very, very often, smart contracts rely on time and timing of when to start and when to start paying. Things like coin offerings are very often based on a particular date and time for the payments to begin or for the tokens to be issued. It is possible to manipulate and exploit that time. So the timing is done on smart contracts with the epoch time. So timing and the way that the contract interacts with time is very crucial. So you do want to go through your battery of tests and validate that your time when your contract can actually execute is correct and the time logic is correct. The other thing is that the timing, this is a date and time here, it's called the epoch time. It can get confusing because it's a long number. So we want to make sure that when we test this, obviously, the correct values are used, and when it is finally set to go, that the proper time is updated. Again, it could be confusing, and someone could notice that the timing is wrong and actually access your contract too early. So again, you need to validate the timing. There are more and more tools coming on the market for smart contract auditing. For contract flow analysis, there is a tool called SolGraph, and Sol is short for Solidity. Dynamic code analysis, Mythex, and Manticore. Vulnerability scanning tools, also taint analysis, so looking for any kind of possibilities in low-level code. That's what our taint analysis is doing. And test coverage. So most Solidity tools do come with unit testing, so you can actually validate that all of your functions are being tested. It can run automatically, and it can also help you with regression testing to always validate that your Solidity tests are running as they should be. And it's a good practice, really. This type of security, this type of hygiene is always a good practice, especially for smart contracts, because they do make payments. They can transfer funds, so the more tools, the better, and they can attract, obviously, bad actors. So we want to make sure that this contract is running like it should be, and it's well audited in case there are problems, so that they can be addressed as quickly as possible. So to summarize, in this lesson, we discussed smart contract vulnerabilities in Solidity. We discussed reentry, access control, denial of service, weak randomness, weaknesses related to timing, and we also reviewed some tools that can help strengthen and find problems and vulnerabilities with our Solidity smart contracts. Our next session will be security alternatives in DLT architecture. DLT stands for distributed ledger technology. That is a blockchain is an example of distributed ledger technology. And please consult your training materials for information on tutoring, private tutoring, and coaching. And thank you again for watching this video. This video is a presentation of coding boot camps.